In this video, we're going to discuss heat changes. Heat changes is talking about the thermal energy that goes into or out of a material. Those commonly change the temperature, though not always. We'll discuss some of those differences. Heat changes come in a couple of fashions. Most often we use it for calorimetry. Calorimetry, measurement of the calories, the heat energy. Q equals ms delta T. Q is our energy, specifically our heat energy. M is our mass. Delta T is our change in temp. And S is our specific heat. Sometimes a small c will be used. Just depends on your book. But what is specific heat? Specific heat tells us the amount of heat energy needed for that material to get hotter. Remember that 1 calorie, the definition for our early energy unit, was 1 gram of water going up 1 degree Celsius. Water requires 1 calorie of energy for 1 gram of it to go up 1 degree. Other materials take quite different energies. As a series of examples here, if we want to look at S values, water, if we do it in joules, 4.184 joules per gram degrees Celsius. If we want to look at a couple other materials, let's look at copper, iron, silver, lead. So we have water versus a series of metals. Well, if you ever had copper cookware, they get hot real fast. Part of the reason why is that it takes 0.387 joules per gram degrees Celsius for copper to heat up. Less than a tenth. It just takes significantly less energy to get copper hotter. Iron, 0.4498 joules per gram degrees Celsius. Silver, 0.235. And lead, 0.128 joules per gram degrees Celsius. The metals just take significantly less energy than water. Water is actually one of the higher specific heats. It takes a lot of energy to heat water up, which means it also has to lose a lot to cool down. This is a nice advantage for life. You can get exposed to something cold, and you'll be reasonably resistant to freezing if you can get out of it fairly soon. If you were made of copper primarily, you'd cool down almost instantly. Additionally, it also keeps us from getting hot too quickly. You can only add energy so quick from the sun, so your body doesn't overheat as long as you can get to shade fairly quickly. Now you know this is all significantly different. They actually change a little bit if you get out of grams and into moles. So water, 18.016 grams in 1 mole. Do this for copper and iron and the rest. You'll find it is 75.35 joules per mole degrees Celsius for water. It's 24.6 for copper. It is 25.12 for iron. It is 25.35 for silver. And it is 26.52 for lead. If you actually look at it as a per mole, we see that the metals are actually fairly similar to each other instead of per gram. Part of this comes from what the heat changes are actually doing. If I have a solid, it's rigidly locked in place. Those molecules don't go anywhere. When they pick up more thermal energy, they just vibrate more. They shake around and they bounce into each other, but they don't move anywhere. Well, as a result, you don't have to put a lot of energy in just to get them to shake more. But the more they shake, the greater their friction, the more they can transfer heat. And so their temperature which is a measure of the transfer of heat, goes up very quickly. A water molecule, on the other hand, as it gets more energy, several things happen. You can vibrate, but there's a couple different ways you can vibrate. You can have your atoms go in and out so that you get longer and shorter bonds as they kind of bounce back and forth. Then they'll go the opposite direction. You'll end up with the other one longer and the other one shorter. Basically, put both your arms out, except hold one of them near your chest, and then go back and forth. So if your right's near your chest and your left one's out, bring your left one in and your right one out, and just do that back and forth. They're moving in opposite directions. You can also have motions when you have water molecules where they bend in and out at the same time. And so have your hands in front of you, a couple, say a foot from your chest, push them both out, and then pull them both in, and then push them both out. This is a synchronous motion. You can have synchronous and asynchronous motions. You can have swirling, so you can just have the molecule kind of spinning, where the whole thing spins around. This is a rotation. Basically, there's a lot of motions water can have that atoms in a solid metal can't. As a result, there's just a lot of places to dump that energy that doesn't net a bigger friction interactions. And so water needs, as we can see, about 3 times more energy per mole in order to go up 1 degree. It just has many other places to put that energy that don't translate well into friction and temperature changes. Calorimetry is a great way to track the energy of a reaction. If you do a reaction in water and you see the temp change of water, you can determine how much energy was released by that reaction. Let's take a look at it. I have 10 grams of water, and I add X compound and Y compound together, and they form compound Z. Water was at 25 degrees Celsius, and it goes up to 63 degrees Celsius. Well, assuming the majority of my material is water, we can pretend that the little bit of heat energy that X, Y, and Z would require is probably small compared to my water. Usually you have a big container of water and then only just a little bit of chemical. So the vast majority of the energy went into the water. We can find Q of the water, which is going to be pretty darn close to the total heat energy. Well, what is Q of water? It's the mass of the water, the S value for water, and the delta T. We were told the mass of the water, it was 10 grams. S value for water, well, we actually know it for calorie. It's 1 calorie for every gram degrees Celsius. But we don't do most of our work in calories. We do it in joules. It is 4.184 joules per gram degrees Celsius. 4.184 joules, grams degrees Celsius. And our delta T, our change in temperature. Well, delta T is always going to be your temp final minus your temp initial. We ended at 63, we started at 25, so 38 degrees Celsius positive. Multiply those together, we will find 1,590 joules. We can find the actual energy that must have gone into our water to make it get hotter. If we are assuming that the reaction is what gave it away, if we made sure it wasn't being heated on the stove, we just threw the chemicals in, they reacted and raised the water temperature to this, then this must be the energy that reaction gave away. Similarly, if we just put 10 grams of water in a pot on the stove and it got hotter, this would be the energy that went into it from the stove. This is just the energy to make the water get hotter. Let's do a practice. 2,000 joules is added. Find final temp. In this case, we're going to have a pot, and it has some water in it. We're going to say that this is a 500-gram iron pot, and it has 100 grams of water. And we're going to start at 20 degrees Celsius. Well, what's happening here is I really have two materials. If I'm putting in energy, if I have a flame or a stove or something else, it's heating up my pot. Well, the water and the iron are in contact. They're both on the stove. Two things that are in contact, you're heating them up, they're going to have the same temperature. At least if you give them a moment to kind of interact. And so our iron and our water must both be at our final temperature. So I have two parts to consider here. I know Q equals ms delta T, and one of these could be the Q of the iron, is the mass of the iron, the S value for the iron, and the delta T for the iron. One of these, I'm going to do the water in green, Q of the water is the mass of the water, the S value of the water, and the delta T of the water. Well, I only have so much energy to put in, so my Q total must be what goes into both of them. I only have 2,000 joules. It's going to spread out between the two materials. So I could rewrite this a little bit. My Q total must equal the mass of the iron, the S value of the iron, and the delta T of the iron, plus the mass of the water, the S value of the water, and the delta T of the water. Conveniently for us, well, they started at 20 degrees, and as long as they're in contact on the stove, they're going to be the same temp. The iron gets hotter, and it's touching the water, so the water gets hotter. If either of them was ever colder, it would heat up the other one. And so they're going to be the same final temp, which means delta T must be the same. Our delta T of water and our delta T of iron must be identical. They're just times delta T. So we can start changing a little bit. 2,000 joules must equal 500 grams for the iron, 0.4498 joules per grams degrees Celsius for the iron, plus 100 grams for the water, and 4.184 joules per grams degrees Celsius. And both of these must be multiplied by delta T. So they each would have had delta T on their own, which means we could have pulled it out and put it on the outside. Do a little bit of math. 500 times 0.4498. We'll find that there's 224.5 joules degrees Celsius. The grams will have canceled when we multiplied. Plus 418.4 joules degrees Celsius. We can add these together, and we will find 642.9 joules degrees Celsius. Delta T must equal 2,000 joules. So we took the Q that would be the iron and the Q that would be the water, and we said they must add up to 2,000. And they have the exact same delta T. So we can pull delta T out of both of them, add up the center bits, and then divide across. Divide by 642.9 joules degrees Celsius. Divide by 642.9 joules degrees Celsius. This is going to give us a degrees Celsius is equal to our delta T. We'll find that 3.11 degrees Celsius is delta T. Our starting temp was 20, and so 20 plus 3.11 for 23.11 degrees Celsius, basically about 23 degrees Celsius. 2,000 joules was enough to heat this small amount of water and the kettle it was in up 3 degrees. So nowhere near boiling yet. I'm going to have to do this for a while more. But this was how we could take several different materials and say, well, what is the amount each is being heated up? How do they work together? The 2,000 joules must be spread throughout them such as to keep the delta T the same. And so we are able to calculate out what that delta T is.